Hello everyone and welcome to this presentation. My name is Grigorios Kostopoulos and I am representing the National and Capodistria University of Athens. Today I will be presenting our research on the shape recovery behavior of PETG structures in 4D printing. In this study, we investigate how fused deposition modeling process parameters influence the shape memory capabilities of PETZ, aiming to optimize its recovery performance for smart engineering applications. So, why focus on this? Shape memory polymers have the unique ability to recover their original shape after being deformed simply by applying heat. However, when we use FDM 3D printing, we aren't just creating a shape, we're creating a complex anisotropic microstructure. The printing path, layer adhesion, and thermal history all play a huge role in how well the material can remember its shape. Understanding these parameters is essential if we want to move from simple prototypes to reliable 4D printed actuators, deployable systems, and smart structures. Our primary aim was to quantify these effects using a robust Taguchi design of experiments. Test this behavior, we followed a standardized thermomechanical cycle, which you can see outlined here. First is the programming step, where we heat the specimen to its deformation temperature, TD, and mechanically bend it into a temporary C shape using the fixture shown in the bottom photos. Second is the fixing step, where we cool the beam down to room temperature while it is still constrained. This locks the temporary shape in place. And finally, for recovery, we place the sample in a water bath heated to the recovery temperature, TR, and without any external load, the internal stresses release freely and the material attempts to return to its original flat shape. Because there are so many variables in 3D printing, testing every combination would take forever. Instead, we used a Taguchi design of experiments. This allowed us to investigate six different control parameters simultaneously. The printing speed ranging from 50 to 150 millimeter per second, layer height from zero point 0.1 to zero point 0.3 millimeters, layer width, nozzle and bend temperatures, and finally, for the last column, we have the deformation or recovery temperature. It is important to note that for this study, we coupled these two values. This means that for each experimental run, the temperature used to deform the beam was identical to the temperature used to recover its shape. That is, both the temperatures were at 88, 92, or 96 degrees Celsius. The table on the bottom shows the 18 specific experimental runs we conducted to cover this design space efficiently. For the specimens, we printed rectangular beams with a length of 95 millimeter, width of 15 millimeters, and height of 2.4 millimeters using PETZ filament. All specimens were printed flat and then mechanically programmed using the custom bending fixture you see in these images. Crucially, every specimen underwent the exact same cooling and stabilization procedure, to ensure that any difference in the recovery was due to the printing parameters, not the testing method. To quantify the results, we define the recovery ratio. We measured the arc height of the beam before and after the recovery, and essentially, a recovery ratio of 1 would mean perfect recovery to a flat line. Our goal was to maximize this ratio. Now for the most important part, the results. On the left, you see the main effects plot for means, and on the right, the signal to noise ratio plot. In the signal to noise ratio plot, the larger is better here means that points with higher values produced more efficient and robust recovery. I have highlighted the optimal settings that can produce more robust shape recovery with red circles. We observed for printing speed a sharp peak at 70 millimeter per second. As speed increased beyond this to 130 and 150 millimeter per second, the performance dropped significantly. This suggests that very high speeds may introduce defects or poor bonding that hinders recovery. For layer height, there is a clear sweet spot at zero point 0.2 millimeter. Thinner and thicker layers both performed worse. Interestingly, the lower nozzle temperature of 230 degrees Celsius and a bed temperature of 70 degrees Celsius and the formation and the recovery temperature of 92 degrees Celsius yielded the best stability. One final observation, layer width shows a relatively flat response compared, for example, to printing speed, and this indicates that layer width is less critical, giving us more flexibility in design without sacrificing shape memory performance. In conclusion, this study demonstrated that the manufacturing strategy plays a massive role in 4D printing performance. The Taguchi design successfully identified the dominant parameters by using the optimal combination, which involves a printing speed of 70 millimeters per second, a layer height of 0.2 millimeters, and a nozzle temperature of 230 degrees Celsius, we can achieve significantly higher and more consistent shape recovery. Finally, the study highlighted that this process is complex. The strong parameter interactions mean that you cannot just tune one variable in isolation. The thermal history defined by the combination of speed and temperature is key. For future work, we plan to investigate the fatigue life of these program structures to see how consistent the recovery duration remains over multiple actuation cycles and to develop a numerical simulation for the shape recovery behavior. Thank you for your attention.